So, hello friends. Today we will start our next unit, that is infinite series. Okay. So this unit is very much based on our last unit, that is sequences. Okay. If you understand the topic sequences properly, then the series topic will be very simple. Okay. So now we will see some introduction about series. Okay. We have seen series many times in our general undergraduate education. Okay. So we know the series. Suppose series say xn. Okay. This is the general notation of infinite series. Okay. Series n is equal to 1 to infinity xn. The series is infinite because the sum is infinite. There are infinitely many terms in that summation. Okay. Suppose now series say k is equal to 1 to infinity. What is this series? This series look like equal to 1 to k is equal to 1. So plus 2 plus 3 plus 4 up to so on. This is the infinite series. Okay. So we are going to focus on infinite series only. Okay. So we have seen so many finite series, so we don't need to study now finite series. Our focus is infinite series. Okay. So these series like these are called infinite series. So general definition of infinite series is the notation is series xn, sum of xn, where n that is from 1 to infinity, which is like x1 plus x2 plus x3 up to so on. Okay, this is called infinite series. Okay, for example, this is the series is equal to sum of all natural numbers. If we take sum of the first n natural number, then series will be finite series. But we are taking sum of all natural numbers, and all natural numbers are infinite, so series is infinite. Okay. So next example is a series 1 by n is equal to 1 to infinity. The again example of infinite series. Okay. So this series looks like 1, 1 by 2, 1 by 3, 1 by 4 up to so on. Okay. This is the infinite series. Sum of reciprocals of all natural numbers. Okay. So this is the general notations, okay, of the series. So next point is sequence of partial sum. So we know, I already said that this series is very much based on the sequence. So whenever there is series, we will find something from sequence to prove whatever they are asked about the series. Now, sequence of partial sum. Okay, suppose this is our series xn is equal to 1 to infinity. Now, we have to find the sequence of partial sum for this series. Okay, so we will form a sequence. Okay, so suppose we define a sequence Sn such that the first term of the sequence is x1. Okay, this series is like this. The first term will be our x1. Okay, we will define sequence. The second term will be this x1 plus x2. Third term will be s3 will be x1 plus x2 plus x3. Continuing in the same way, the n term of the sequence will be sum of first n elements. So x1 plus x2 up to xn. The sequence, this sequence whose terms, first term is x1, second term is x1 plus 2, n term is this. So this sequence whose n term is this element is called sequence of partial sum for this series. So for this series, this is the sequence of partial sums. Okay, whose n element is the sum of first n elements, so that they are said partial sums. Now this is the total sum. So it is a series, but we are defining a sequence which contain a n term. The n term is sum of first n elements. So this sequence is called sequence of partial sum for this series. So n term for this sequence is the sum of first n element. Okay. Then there is the one criteria or definition that says that this, again the point is we are seeing sequences are either convergent or divergent. Similarly, series are also convergent or divergent. And first basic criteria for series to be convergent is their sequence of partial sum is convergent. If for series its sequence of partial sum is convergent, then series is convergent. So see, to basic criteria is to verify whether series is convergent or not. We have to verify whether the sequence of partial sum for that series is convergent or not. So everything comes to again sequence. If sequence of partial sum for this series is convergent, then series also convergent. Okay, this is one of the basic criteria for series to be convergent. Okay, so the definition of convergent series is the series xn n is equal to 1 to infinity is convergent if, I already said the series is convergent if its sequence of partial sum, its sequence of partial sum Sn, okay, Sn is its sequence of partial sum is convergent. Okay. So series is convergent if its sequence of partial sum is convergent. That is, limit of sequence exists. That is, limit of sequence Sn is equal to say S exists, and this limit S is called sum of this series. Okay, so summation of xn, that is sum of x1 x2 up to xn, this sum is said to be equal to S if limit of the sequence of partial sum is exist and it is S, then this S is called sum of this series, and series is said to be convergent. Okay, and this S is called sum of the series xn. Okay, if limit of sequence of partial sum does not exist, then the sequence of partial sum is divergent, and so series is divergent. Okay, so if limit of if Sn is divergent, where Sn is the sequence of partial sum for this series, then our series is not convergent. That is, then series is also divergent. Okay, and divergence to plus or minus infinity. So this is the first criteria for convergence of series, and that is, if sequence of partial sum for the series is convergent, then this given series is convergent, and then limit is said to be sum of this series. Okay? We will see some examples. Okay, now, so first example we will see. Consider the series minus 1 raised to power n, and n is equal to 1 to infinity. Okay, so we have to first check whether the sequence of partial sum for this series is convergent or not. Okay, so we will find the sequence of partial sum Sn. So n term of the sequence of partial sum is equal to, take the sum of first n elements. So first element will be minus 1 raised to power 1, so minus 1. Second element will be minus 1, so plus square of, put n is equal to 2, so square of minus 1, so plus 1. Third element will be cube of minus 1, put n is equal to 3, so cube of minus 1, that is minus 1 over 3, it's minus 1. So minus 1 plus 1 minus 1 plus 1 continue. Okay, up to minus 1 raised to power n. Depend on the value of n, the last term. If n is equal to 2, then S2 will be minus 1 plus 1. If n is equal to 3, then S3 will be minus 1 plus 1 minus 1. Okay. So depend on the value of n, it is either equal to plus 1 or minus 1. If n is even, okay, put n is equal to 4. So S4 will be minus 1 plus 1 minus 1 plus 1. So it is equal to minus 1 plus 1 0 minus 1 plus 1 0. So S4 is 0. If you take n is even, this sum will be equal to 0. And if you take n is odd, so it is 3. So minus 1 plus 1 minus 1. So minus 1 plus 1 0, 0 minus 1 minus 1. Okay. So you will get minus 1. So this sequence Sn is equal to 0 if n is even, and it is equal to minus 1 if n is odd. So see, the sequence Sn is equal to 0 if n is even, and it is equal to minus 1 if n is odd. So this our sequence Sn tends to 0 if n is even and has a limit minus 1 if n is odd. Okay, because sequence is constant sequence, either 0 or minus 1. So yeah, when n is even, sequence converges to 0. When n is odd, sequence converges to minus 1. But if sequence has a limit, it must be unique. So this implies the sequence Sn of partial sum. Okay, the sequence Sn of partial sum is not convergent. Is not convergent. The sequence Sn of partial sum is not convergent. So the given series minus 1, sorry, n is equal to 1 to n minus 1 raised to power n is not convergent. So it is divergent. Okay. Why? Because sequence of partial sum corresponding to this series is divergent. So this series is divergent. Okay. So we will take another example. So okay. So example 2. Okay. The sequence given by, so series given by series of sum of squares of natural number n is equal to 1 to infinity. Okay. So what will be Sn? Sn will be sum of squares of first n natural number. Okay. So Sn will be 1 square plus 2 square up to n square. This is the sequence of partial sum. Okay. Because n element is the sum of first n elements. Okay. So the sequence of partial sum for this series will be 1 square plus 2 square plus to n square. And you know the formula for calculating the sum of squares of first n natural number. So this is equal to n into n plus 1 into twice n plus 1 upon 6. You know this formula for sum of squares of first n natural number. Okay. But as n tends to infinity, this twice n, this all in the event there is n, that is we will get n cube. So as n tends to infinity, Sn also tends to infinity. So the sequence is divergent. The sequence of partial sum for this series is divergent. So this series of sum of natural squares of natural numbers n is equal to 1 to infinity is also divergent. Okay, it is also divergent. Why? Because the sequence of partial sum for this series is divergent. Okay, so this is one of the basic criteria for the series to be convergent or divergent. What is the criteria? If sequence of partial sum for the given series is convergent, then the series is convergent. Otherwise, it is divergent. Okay. So on this criteria, that is the sequence of partial sum is convergent implies series is convergent. We will see another example. Okay. So the example is take the convergence of this series. See the series 1 upon x into x plus 2 upon plus 1 upon x plus 2 into x plus 4 plus 1 upon x plus 4 into x plus 6 up to so on. So infinite series. Okay. So we have to check whether this series is convergent or not. Okay. So here the series is directly given in terms of element. Okay. Sometimes series will be given in n term, that is series of xn. Okay. Sometimes series will be given in 11 form, that is some 2-3 terms will be given. Okay. So here x is real number and which is not equal to the 0, a non-zero real number. So here the series summation of the terms. Okay, so here we can write also this series in the form this series of xn, where x1 will be equal to, here x1 is equal to this term. Okay, so 1 upon x into x plus 2. But we can write this term in another manner also. See, this is also equal to 1 by 2 of half of 1 by x minus 1 upon x plus 2. See, if you do the calculation, this will be equal to the x plus 2. Okay, so x plus 2 into 1, so x plus 2 minus x upon 2, so x plus 2. Okay, so this will be upon x into x plus 2, and this is half. Okay, so this x and x get cancelled. Okay, so 2 get cancelled, so remains only 1 upon x into x plus 2. Okay, so this implies 1 upon x into x plus 2 is equal to 1 half into 1 by x minus 1 upon x plus 2. Okay, so in the similar manner we can also write this term, and all terms. Okay, so here x2 is equal to 1 upon x plus 2 into x plus 4. Okay, and this is equal to again half of 1 upon x plus 2 minus 1 upon x plus 4. Okay. Later on, the term x3, which is equal to 1 upon x plus 3 into x plus 4 into x plus 6. This will be equal to half of 1 upon x plus 4 minus 1 upon x plus 6. So continuing in this way, our n term will be, so xn will be equal to, see, in first term here is x plus 2, in second term here is x plus 2 x plus 4, so in second term here is 4, so 2 times 2, here 2 times 3 in third term. Okay, now 2 times 3 and 2 times 2. Okay, you see the third term, 2 times 3 in third term, here 6 is x plus 6, and 6 comes as 2 times 3, and 3 also the third term, 3 minus 1 2, so 2 into 2 is 4. Okay, similarly in second term, since it is second term, this will be 2 times second term, so 4, 2 minus 1 1, so 2 into 1 2. This is the pattern for this series. So n term will be equal to 1 upon okay, x plus, since it is n term, in the first bracket there will be n minus 1 times, so 2 times n minus 1 x. Okay, since, see, it is third term, so 2 into 3, so it is n term, so 2 into n minus 1, so x plus 2 into n minus 1. Okay, x plus 2 into n minus 1, or we can write in curly bracket. Okay, so x plus 2 times n minus 1, this is the one bracket. Okay, plus, into x plus, simply it is n term, so 2 times n. Okay, it will be equal to x into 2 times n. Okay, this will be our nth term of the series, and this will be equal to the 1 half. Okay, into 1 upon x plus 2 times n minus 1 minus 1 upon x plus twice n. Okay, so this is the first term, second term, third term, and up to this is the nth term. Now our sequence of partial sum. Okay, Sn is nothing but sum of first n term. So Sn is nothing but x1 plus x2 plus x3 up to xn. Now, if you observe the pattern in this sequence, the first term is here, so half is common everyone. So sum there will be half will be common. Now see, here is 1 by x minus 1 upon x plus 2. So minus 1 upon x plus 2, and here 1 upon x plus 2. So half is common also. So minus 1 upon x plus 2, and here plus 1 upon x plus 2 will get cancelled. So here minus 1 upon x plus 4 and plus 1 upon x plus 4 will get cancelled. This minus 1 upon x plus 6, and in the fourth term you will find plus 1 upon x plus 6. Okay. So this the only term remain is this first and this last term. Okay. This term will be cancelled in the xn minus 1 terms. Okay. So it will be here minus 1 upon x plus twice n minus 1, and it is plus 1 upon x into twice n minus 1. So this and this term will get cancelled. So remains only minus 1 upon x plus twice n. And this one half is common. So after summation, the remaining part is only half of 1 by x minus half of 1 upon x plus 2n. So half is common. So only 1 upon x plus twice n. Okay. So this is our Sn. Now we will take the limit of Sn. So limit n tends to infinity of the n term of the sequence is equal to, so 1 half is common, is was outside, 1 half into limit n tends to infinity 1 by x minus 1 upon x plus twice n. Okay. So as n tends to infinity, this twice n tends to infinity, so x plus infinity tends to infinity, 1 by infinity tends to 0, this term tends to 0 as n tends to infinity, and in this term there is no n, so it is remain constant as 1 by x. So limit becomes half into 1 by x, that is 1 upon twice x, because this term goes to 0 as n tends to infinity, this twice n tends to infinity, so x plus twice n tends to infinity, so 1 upon infinity tends to 0, this 1 by x and this is as it is, so 1 by 2 into 1 by x, 1 by twice x. So limit of Sn is equal to 1 upon twice x, and here x is a real number not equal to 0. Okay, and this is not equal to 0. See, x not equal to 0. 1 upon twice x is again a real number. So this implies the sequence Sn of partial sum, sequence Sn of partial sum is convergent. This implies the given series is also convergent, and the sum of this series is equal to 1 by twice x, and sum of this series is 1 upon twice x. Okay. So this series is convergent, and this sum is converges to 1 upon twice x. Okay. This is the application of convergence based on sequence of partial sums. Okay. Now we will see necessary condition for the convergence of the series. And the condition is, if the series xn is convergent, then its limit of n term of the series is equal to 0. This is the theorem which says necessary condition for the convergence of the series xn is that limit of n term of the series is equal to 0. Okay. Now see, this is the only necessary condition. Okay, and not sufficient condition. So we'll come to this one later. Suppose first we will prove this necessary condition. Okay. So this condition implies that there is some series xn, and if limit of xn is equal to 0, then series can be convergent. Okay, but it does not give the guarantee that series is always convergent or not. Okay, so we come to that point that okay. So first we will do this theorem. So let series Xn is convergent. Okay, some L from n is equal to 1 to infinity. So suppose series Xn is convergent. So we know criteria that if series is convergent, then the sequence Sn, which is the sequence of partial sum, which is nothing but the sum of first n term of the series, which is equal to x1 plus x2 plus x3 up to xn. Since series is convergent, the sequence Sn of partial sum is convergent. So this implies limit of this n term, say Sn, it exists, it is a real number. So so we can give, so this implies limit of sequence exists and it is some real number. So we can give notation for the real number, we can give in notation. Okay, so we see that, so limit of Sn exists and is equal to say yes. Okay, now we have Sn is equal to x1 plus x2 up to xn, and limit of the sequence of partial sum exists and it is equal to yes. So sequence Sn is convergent, so limit of the term Sn minus 1 also exists and it must be equal to yes. Why? Because in sequence Sn is convergent and its limit is yes, limit of Sn minus 1 also equal to yes. Okay, now we have Sn is equal to, okay, so we know for the n term of the sequence Sn is equal to x1 plus x2 plus x3 up to xn minus 1 plus xn. Okay, this is the Sn. What will be our Sn minus 1? Sn minus 1 will be sum of first n minus 1 element of the series. So up to this is nothing but Sn minus 1. That is sum of first n minus 1 element. This implies our Sn is equal to Sn minus 1 Sn minus 1 plus this remaining xn. Okay, so from this we can say that limit of Sn is equal to limit of this term is equal to limit of Sn minus 1 plus xn, but we know limit of the Sn plus Tn is equal to limit of Sn plus limit of Tn. This is the general formula. So here limit of this is equal to limit of Sn minus 1 plus limit of xn, and here LHS as it is limit of Sn, but limit of Sn is yes, so it is yes is equal to what is limit of Sn minus 1? It is also equal to yes plus limit of xn. Now take this yes to left side, so it becomes minus yes. So here yes minus this yes becomes 0. So this implies 0 is equal to limit of xn. So limit of xn is equal to 0. So necessary condition for the series to be convergent is that the limit of n term of the series must be equal to 0. But okay, this is the proof. But the theorem says this is just the necessary condition and not sufficient. This means if limit of sequence is 0, then sequence may be convergent, but it does not give the guarantee. But this gives us one very important criteria for the series to be divergent. Okay, since what this theorem says, if sequence is convergent, then limit of n term is equal to 0. So taking its contrapositive, this theorem says if we take contrapositive of this statement, we get if limit of n term is not equal to 0, then the series Xn is divergent. taking controversy. What is the statement? Series xn is convergent if limit of xn is not equal to 0. So its controversy is if limit of xn not equal to 0, then series xn is not convergent, that is divergent. So this gives one test for divergence of the series. If there is some series whose limit of n term is not equal to 0, then it is confirmed that that series is divergent. Okay, so it will be very helpful to us in solving the problems for testing the convergence or divergence. If limit of n term is not equal to 0, then definitely that series is not convergent. But if limit is equal to 0, there are chances that series is convergent. Okay, but it may happen that there is some series whose limit of n term is 0, but series is not convergent. That can happen. Okay, so limit of this n term equal to 0 says the sequence may be convergent or divergent, but limit of the series not equal to 0 directly says that the series must be divergent. Okay, so this is the application of this theorem. Okay, we will give one example in which limit of n term is 0, but still series is not convergent. Okay, so from that we will understand that this condition is just sufficient, is just necessary, not sufficient. Okay, we now suppose consider the series xn where n is equal to 1 to infinity given by where xn is equal to 1 by n. That is series nothing but series of reciprocals of natural number, sum of all reciprocals of natural number. This series is equal to 1 plus 1, so n is equal to 1 to infinity, and this is equal to 1 by 1, so 1. Then put n is equal to 2, so 1 by 2 plus 1 by 3 up to somewhere 1 by n up to so on. Okay. Now what is the sequence of partial sum for this series? The sequence of partial sum for this series will be sum of first n elements, and this is equal to this up to 1 by n. This continue up to so on. So Sn will be sum of first n terms. So this is equal to 1 plus 1 by 2 plus 1 by 3 up to 1 by n. And we have seen in the unit sequences that sequence whose n term is not convergent. We are just seeing Cauchy sequence that this sequence is not Cauchy sequence. This sequence is not convergent. So sequence of partial sum is not convergent. This implies this series is not convergent. But here the n term is 1 by n. Here n term xn is equal to 1 by n, and its limit as n tends to infinity is equal to 0. As n tends to infinity, 1 by n tends to 0. So here we get a sequence xn whose n term is 1 by n and which tends to 0. That is limit of n term is 0. Still the series is divergent. Okay. So this says this criteria is only necessary condition. It is not the sufficient. So from this we can say if there is a series xn and if limit of xn is not equal to 0, if limit of xn not equal to 0, then series is always divergent. But if limit of xn is equal to 0, then series may be convergent or divergent. Okay, so we have to further investigate in that case. So if limit of the series not equal to 0, it is confirmed that series is divergent. But if limit of the series equal to 0, the series may be convergent or may be divergent. Okay, depend on last sufficient condition for the convergence of the series. We will solve some example. Okay, the question is test the convergence of the series xn. Okay, in the following examples. So first example is that the n term is given xn is equal to n plus 1 upon n plus 2. So we know the criteria. Our criteria is to find the limit of n term of the series. Okay, so here xn is given. So limit n tends to infinity of xn is equal to limit n tends to infinity of n plus 1 upon n plus 2. Now we will divide numerator and denominator by n. So this become limit n tends to infinity, divide numerator by n. So n by n is 1 plus 1 by n. Also divide this by n. So separating, we get n by n is 1 plus 2 by n. So as n tends to infinity, 1 by n tends to 0, 2 by n tends to 0. So 1 plus 0, 1 plus 0. This is equal to, as n tends to infinity, 1 by n tends to 0. Also, as n tends to infinity, 2 by n tends to 0. And limit of 1 is 1, the limit of this 1 is 1. So 1 by 1 is equal to 1. And the limit of the n term is not equal to 0. And we have just seen, if limit of the n term of the series is not equal to 0, then series is divergent. This implies this series whose n term is this is divergent. Okay. Now next series. So here x n is equal to cos of pi by n, and limit of this n term cos of pi by n as n tends to infinity. So as n tends to infinity, pi by n tends to 0. So this becomes cos of, as n tends to infinity, this pi by n tends to 0. This becomes just cos of 0 is equal to 1, and 1 is not equal to 0. Okay. So again we get the series whose n term has a limit non-zero. So by our criteria, this series whose n term is cos of pi by n is again a divergent. This is also divergent. Now the series whose n term is 1 plus 1 by n raised to power n. Series xn whose n term xn is 1 plus 1 by n raised to power n. So now limit of n term, that is limit of 1 plus 1 by n raised to power n as n tends to infinity. We know this limit, it is equal to e, where e is a number lies between 2 and 3. So again it is not equal to 0. So our criteria, the series whose n term is this is also divergent. Okay. Now the next example is the series xn whose n term xn is n sin inverse 1 by n. So again our target is just to find the limit of this n term. If limit not equal to 0, series is divergent. If limit is equal to 0, then we have to further investigate whether the series is convergent or divergent. So limit of xn. So limit n tends to infinity of xn is equal to limit n tends to infinity of this n term, that is n sin inverse 1 by n. Okay. Sin inverse of 1 by n. Now we can make some adjustment here. This is equal to limit n tends to infinity. This sin inverse 1 by n as it is. This n we can write as 1 upon 1 by n. Okay, because 1 upon 1 by n is same as just writing n. Okay. Now as n tends to infinity, 1 by n tends to, okay. So before that we will write this 1 by n as theta. Okay. Suppose let 1 by n is equal to theta. So as n tends to infinity, 1 by n tends to 0, but 1 by n is equal to theta. So this implies theta tends to 0. See, as n tends to infinity, 1 by n tends to 0, but theta is equal to 1 by n, so theta tends to 0. So replace 1 by n by theta and limit n tends to infinity by limit theta tends to 0. So this is equal to limit, this implies limit of xn is equal to limit n tends to infinity. Now n tends to infinity becomes theta tends to 0. Theta tends to 0. Sin inverse of 1 by n, but 1 by n is theta. Sin inverse of theta upon 1 by n is theta. And we know limit of x tends to 0, sin inverse x upon x is equal to 1. We know this standard formula. This implies limit theta tends to 0 of sin inverse theta upon theta is equal to 1, which is not equal to 0. So again, limit of this n term is not 0. So series whose n term is this is also divergent. Okay. This is the application of the sufficient condition, sorry, necessary condition, that we have seen that if limit of the end of the series is not equal to 0, then series is divergent. Okay. So thank you. Hope you understand this concept of series and the criteria we have seen for convergence and divergence of the series. Okay.